accelerating downward relative to 4 times x. So the things that I'm interested in are velocity, and then when it reaches plate B, so this is like position. Okay, so velocity and position are pretty much the only things that I'm interested in. So I'm not interested in time. Actually, that's my formula sheet here. So if I go to this, time. Oh wait, this one has everything I need. You guys can see here. So this one has everything I need: acceleration, velocity, and position. Okay. So I went ahead and started with that one. And then I plugged it in. And once I plugged it in, then you rearrange it. And then what you do is you integrate it. Okay, so you do that kind of hybrid form of integration to get, and I found out what this was. I'm tutoring someone in Calc 2 at UT, and this is, it's indefinite if you don't have the limits, it's definite if you have both limits. I think this is just called the fundamental theorem of calculus, if you have like the variable on top and the bottom, but anyway, that's what her teacher called it. So then when you integrate it, you evaluate it between those 2 points. And if I've made a mistake, you guys catch my mistake here. And so then you just plug in the variable and the boundary condition. And then you just have an equation that is velocity and position, and I just simplified it and plugged in x is equal to 0.2. Was up, yeah, x was starting was up, down. So x was equal to 0.2 was at the bottom plate, and then I just found that velocity. We will do these types of integration problems again, but instead of x, v, and a, we'll have theta, omega, and alpha. What if it had been, and I was looking for v at x is equal to 0.2 again. How would that have changed? Would it have changed the equation that I would have used initially? Like up here? What was the question? Oh, if I had been given you acceleration as 1 over v instead of 4 times x.
It would have changed one side.
Yeah, so it would change that side, right? Because I'm still kind of looking for the same things. Velocity is a function of position, and acceleration was a function of velocity this time. So that would have been 1 over v is equal to v dv dx. Okay, separate all the x's and v's on one side. So this would have been dx is equal to v squared dv. Okay, and then you would just integrate between the upper and lower limits, and then kind of move on. So, what if instead, if I had wanted it as a function of time, then I would have had to have substituted it into this equation. if I had wanted to know the velocity at 0.2 seconds, then I would have said A is equal to dv dt, and that would have been 1 over V is equal to dv, oh, I can't write here, dv dt. And then I would have switched this so that you have dt is equal to V dv, and then gone on. So you just have to, it is changing. So Andrew had asked me, is it kind of like statics where, if I kind of review the previous test, would it be very similar? In statics it is, because you can't be that creative with statics. But here, I could give you acceleration as a function of 3 different things. Okay, and if the example test that I gave you, it was a function of V, you can probably guess it's going to be a function of X on the next one. So kind of alternate it so that it's just slightly different. So as I said, we'll do this again in our rotational dynamics, but instead of our normal alphabet, X, V, A, we'll use theta, omega, and alpha. Okay? But it'll kind of be the same process. We will start with the basic equations of motion here, and then just kind of start substituting. All right. Any other comments? Did I do that right? I was doing it at the same time, so. Anybody finish it? Okay. I'm safe on that one. All right. So then the 2 new coordinate systems were normal, tangential, and radial transverse. So this was an airplane that was moving on in a circular arc, and I gave you the acceleration of the airplane along the path of the arc, as well as its instantaneous velocity at that point. And so to find the acceleration, you had to find the 2 components here. Okay, and so the 2 components were a sub t, which was given, and then the normal due to the change in direction is just that v squared over r. So once I calculated those 2, then the acceleration is just those 2 values. Okay? So they're at 90 degrees to each other. So if I were to look at this plane, the 60.61 feet per second squared is, and that's a 2g term there. So about would be in towards the center, and then this would be 40 feet per second squared. And that is at a 90-degree from each other. So if you wanted to find the total acceleration, how would you resolve those 2 components into a single value and angle?
Square.
So the resultant acceleration would be somewhere in this direction, and its magnitude would be the square root of 40 squared plus 60.61 squared. And then you could figure out, whichever angle if you were interested in the direction of it. And then finally, this last one, this is where you're going to have to check my math. Did anybody finish this one? My process is correct. So we were given theta and r as functions of time. Okay, so just took the first and second derivative of each, plugged in t is equal to 3 seconds for those. Andrew, you looked like you had finished that. Did you get to it?
I'm going through it. I didn't get the same answer.
For the derivatives or the...
I don't know. I just started looking through it because I just realized I didn't have the same answer as you.
Okay, good. So once you do these derivatives and then plug in the time, that's the bulk of the problem there. Then you just go back and you pull the equations for velocity and acceleration, and then pull the numbers in, and then crunch the numbers, and then once you find it in components, then you can solve it, the magnitude of it, by the square root of the sum of the squares. So what do these numbers mean? So we kind of talked about the acceleration up here. So this point, 479. I still haven't, my scanner's on the blink, so I haven't scanned that other problem. But maybe if you guys don't mind, I'll just take a picture and then forward it to you. But the velocity is 0.479, and that shouldn't be in meters per second squared, it just should be in meters per second. And so the radial axis is outward, and then the transverse is perpendicular to that. Okay, so this velocity is moving outward in the radial direction, 0.24 meters per second, and in the transverse direction, 0.4144. Okay, so it's kind of moving out and then up. The acceleration is actually moving outward, but it's slowing down. So the acceleration is inward, that's what that negative means. And it's still accelerating in the transverse direction. Okay, so in those two directions, they're like acceleration is independent of each other. You can separate the two because their description of their positions, their linear positions and angular positions were independent of each other. So again, all of these are things that if you do like 3 or 4 of them, if you do another one of these, it'll click. I'm ready to do things